All right. So this was a problem that we looked at in recitation, and I want to take a closer look at this. All right, so we're told to use nodal analysis in this particular case. So one thing when we do nodal analysis, we need to define a couple of things, right? So here, let's make our ground down here. And I'm going to call this V1, V2, and V3. So those are the node voltages. So V3 is, I guess, VO. All right, but let's just say I called it V3. All right. Now, what I want to do here is remember a little bit about what we're doing, with nodal analysis. So anytime we do nodal analysis, right? So nodal analysis, our basic approach is that we are solving for node voltages. Okay, so we're ultimately solving for node voltages, but we do that by writing KCL equations at each node. And those KCL equations contain the branch currents flowing into those nodes. Into those nodes. Okay? Let me place that. Okay. So to do that in this particular case, right, it's not that hard to do in this particular problem. The issue that I have in this particular problem is the fact that I've got these unknown dependent sources, right? The dependent source makes this a little bit tricky. Whenever I have a dependent source like this, so if I have a dependent source at a node, so in other words, one of my node voltages here, I mean, I'll skip ahead here for a second, but basically V2 equals 2Vx, right? The fact that I have V2 equal to 2Vx is a little bit of a problem, right? What this ultimately means, whatever the dependent source at a node, if I had an independent source at a node, I would know its node voltage right away, and I wouldn't have to write a KCL. Well, in this particular case where I have a dependent source, what this means is that I'm gonna need some other equation, and most likely that equation is going to be some sort of Ohm's law somewhere else in the circuit. Some sort of Ohm's law relationship from somewhere else from elsewhere in the circuit. Okay, so let's see if we can understand that here. So in this particular case, I already know V1 is equal to 6 volts. Okay, that's already set because I have an independent source at that node. All right, I can see that V2, there's no sense in writing a KCL here. I know I did that in class, but I really don't have to. I can say that V2 equals 2Vx. Okay. Now, I don't know what Vx is. That's a little bit of a problem. All right, at node 3, I actually do have to write a KCL equation. So let me just bring the circuit back up. So I'm gonna do it like this. I'm gonna say before I do this, I like to be very careful about this and I'm gonna call this VC. All right, V3 is the node voltage. That's the voltage here. Okay, and so I'm gonna define a current here, I1. All right, I2 and I3 like that. Okay, so at node 3, so again, because I write KCL equations at each node in terms of the branch current flowing into those nodes, I define the branch currents. Okay, so I'm going to say at node 3 I have I1 plus I2 equals I3. Okay, now just in terms, since those are branch currents, I can define those in terms of the Ohm's laws across each component. So in other words, I1 is equal to VC divided by negative J, which is the impedance of the capacitor. I2 here is simply the 2 amps at the top, so the 2 amp source. And then I3 in this case is simply V3, the voltage across that resistor, divided by 1. Okay? Now, in terms of node voltages, I can say that V sub C is equal to V2 minus V3. So notice up here, right? I say VC is equal to the voltage of the plus node minus the voltage of the negative terminal, right? So V2 minus V3. So that means I can rewrite this as 2Vx minus V3. And I can plug everything in here now, right? So this guy goes back into here. I do that slowly because it's very easy to start screwing up signs when I have these, depending on which directions I want the currents to go. I think the simplest thing is just to remember every time I do nodal analysis, I'm writing in terms of branch currents. So for me, I write the branch currents. Then I define those branch currents in terms of the Ohm's laws for the individual components. And then I expand those Ohm's laws into the node voltages. All right? I think that process, maybe it's a little more time consuming, but in the end, tends to give you the right answer, and as a result, ultimately becomes less time consuming. Okay? So let's expand this now. So I1, in terms of the node voltages, is 2Vx minus V3 over negative J plus I2. So what is I2? I2 is 2. And I3 in this particular case is V3 over 1. So V3 over 1. Okay. So now I've got two equations and I've got two unknowns. Now the thing is, for this dependent source, I got to figure out, well, how do I get another equation? Like I said, I need to go create some other equation, and usually it's some sort of Ohm's law. So like we saw in class yesterday, I see, well, my Vx right there, my Vx is across this 1 ohm resistor. So I can see that Vx is equal to V1 minus V2. So the Vx has to be, so I already know V1 is 6 volts. I know that V2 is 2Vx. So now I've got an equation that's going to tell me Vx, right? I can see that basically, what do I have? I have 3Vx equals 6, or Vx equals 2 volts. Okay, so I've got now, from that, V2 equals 4 volts. Okay. Now I need to solve for V3. So to do that, it's pretty easy. I can just go back into this equation. And I can say I've got, okay, so 2Vx is 4. 4 minus V3 over negative J plus 2 equals V3. Right? So now I can sort of solve that guy and say I have V3 plus, on this side, let me go a little bit slower here. So I get 4 over minus J and I get plus V3 over J plus 2. Okay? So I can rearrange that guy to be V3 times 1 minus 1 over J. Okay? So bringing this term over to the other side. That has to equal 2 plus 4 over minus J, like that. Right, now again, I do that, I'm going to solve that guy in MATLAB here real quick. So let me go bring this over here. Alright, so now I'm going to say 2 plus 4 over minus j. We'll call that top. And I'm going to say bottom equals 1 minus 1 over j, like that. So I'm going to say V3 is equal to top divided by bottom. Okay? So basically what I'm saying is V3 equals 2 plus 4 over minus j divided by 1 minus 1 over j, like that. And I've defined this to be top, and I've defined this to be bottom, and I've gone and I've solved for that. So what I kind of like about MATLAB is I can maybe define a little bit more easily these different steps, right, and allow myself to kind of go step by step so I can see the processes a little bit more easily. You know, in your calculator, it's not always all that easy to kind of go back. I know it looks like it is because you can see everything all at once on one line. Although you have to kind of go back and forth. MATLAB makes it a little bit easier to lay that all out and to make changes if you need to. All right, so I run that guy and I get 3, so I get V3. V3 equals 3 plus j. Now we usually don't want our voltages in rectangular form, right? I'd like to get that in terms of polar form. So in MATLAB I say abs of V3. So abs of V3 is the magnitude 3.16, all right, volts. And then I say angle, and since MATLAB does the angle in radians, I say angle V3 times 180 over pi, and I get 18.44 or 43 degrees, I guess. So angle V3 equals 18.43 degrees. Okay. So in the time domain, if I wanted to do that, I'd say V3 of t equals 3.16 cosine omega. Since I don't know what omega is here, I'll say omega t plus 18.43 degrees. Okay. All right. So critical thing in this problem, if I can expand this guy out here again, the critical thing in this problem was, okay, if I'm doing nodal analysis, I need to recognize that I'm solving for node voltages. I'm doing it by writing KCL equations at each node, and I do that, I write those KCLs in terms of the branch currents flowing into those nodes. Whenever I have a dependent source at a node, like I do here, right, I'm going to need to create some sort of other equation, right, from the circuit, right, to be able to do that, right? Another sort of similar example that I'll look at that you guys currently have in 2018, I guess, here on a homework is this particular problem right here, where, again, if in this particular case we're asking you to do mesh analysis, right? And so I clearly with this mesh I can define everything pretty easily. With this mesh similarly. Here's a case where now I have in this third mesh over here I have a current source, right? Well, I know here that what the current is in this mesh. The current in this mesh is 0.75 Vx. It's as if I had a dependent source, right? The only thing is I need to somehow use my results from the other two meshes to create an Ohm's law relationship that will help me to solve for this Vx. That ultimately is what you guys will be able to do to solve this particular problem. Okay? All right, so hopefully that helps a little bit. You know, the mesh analysis is very similar. Whenever I do a mesh analysis and I have a dependent source as one of the known mesh currents, I'm going to need some other equation to be able to tell me how to solve it. All right, same sort of idea.